Hi, and welcome to this next lecture for Math 152. So you have me again, Ben Adcock, and I'm going to be taking you through section 11.9, which is titled Representation of Functions as Power Series. So you were introduced to the concept of power series in the previous section, 11.8, and that section was focused on convergence of power series. And so what we're going to do in this section is we are going to show how we can represent functions as power series for certain regimes, so when the power series converge. You already saw an example of this last time with the function 1 divided by 1 minus x. Now we're going to see how to build representations of more general functions as power series, and this is going to lead you nicely into the next section, section 11.10, where you're going to talk about Taylor and Maclaurin series. Okay, so let's get started, and we're going to start with the following problem. Can the function f of x equals 1 divided by 1 plus x be written as a power series? Okay. Well, you saw this last time, but let me repeat this because it's very important for today's lecture. So let's consider the geometric series. Which is the sum from n equals 0 to infinity of x to the n. So this is the series 1 plus x squared plus dot dot dot. So we know that for this the ratio is x and the first term a is equal to 1. So therefore this series is equal to 1 divided by 1 minus x, and this is for the absolute value of x less than 1. Okay. So this is an important fact that you've already seen and we're going to be using throughout today's lecture in particular. So now let's go back to the function that we're interested in. So we're interested in f of x is 1 divided by 1 plus x. So to write this as a power series, the first thing we do is we write 1 plus x as 1 minus negative x. So now this is just a function in this form with the argument x replaced by negative x. So this we can write as sum from n equals 0 to infinity of negative x to the n, which is equal to the sum from n equals 0 to infinity, negative 1 to the n, x to the n. Okay, so the only thing we need to do, we've written our function as a power series, but we need to determine when this series converges. Okay. So, this converges when negative x, the absolute value of negative x, is less than 1, i.e., which is just the same as saying the absolute value of x is less than 1. So what have we concluded? We concluded that f of x can be represented as the power series, the sum from n equals 0 to infinity of negative 1 to the n x to the n, for the whenever the absolute value of x is less than 1. Okay, so that's the answer to this problem. And you notice here that the key thing we did was to take the function that we're interested in, f of x, and rewrite it in terms of a function whose power series we already knew. Okay, and the function that we'll use throughout today's lecture is 1 over 1 minus x. Okay. So, now that we've done this, it's time to introduce a little bit of terminology. So suppose we have a power series of the form, the sum from n equals 0 to infinity cn x to the n. So as you saw last time, this is the general form for a power series. And let's suppose that this has an interval of convergence I. And for each x in the interval, let's write f of x for the value of the series. Okay. So then what we say is that we say that this power series, so the sum of Cn x to the n, is the power series representation of f of x. Okay. So whenever this series converges, it's equal to the function f of x. And so this is really what we mean by representation here, is we're saying that this is another way, this series is another way of expressing the function f of x. Okay, let's do a couple more examples. So now, these examples, let's find the power series representation of the two functions f and g here. Okay. So again, we're going to think about the series 1 over 1 minus x, or the power series representation of 1 over 1 minus x, which is x to the n, the sum of x to the n. Okay, and this is for absolute value of x less than 1. So let's take our first example. And we're going to follow the same procedure as we did last time. So this is 1 divided by 1 plus 4x squared, which is equal to 1 divided by 1 minus negative 2x all squared. So now this is of the form 1 divided by 1 minus something. So I can write this as the sum from n equals 0 to infinity of negative 2x all squared raised to the power n. And let's separate out the terms here, so we can write this as the sum from n equals 0 to infinity of negative 1 to the n, 2 to the 2n times x to the 2n. So that's our power series representation. What we need to do now is find the interval of convergence. So the first thing we notice is that this equality here, where we rewrote and we used this expression here, this holds whenever the argument, negative 2x squared, is less than 1 in absolute value. So this holds for the absolute value of negative 2x all squared being less than 1. And that's equivalent to 4x squared less than 1, which is equivalent to x squared is less than a quarter, which is equivalent to the absolute value of x less than 1/2. So we've determined now that the interval must include the range x between negative and half and positive 1/2. To find the interval itself, we need to show that this is exactly the interval. So let's observe that if x is equal to 1/2 or x is equal to negative 1/2, then the series, and I should have labeled it, so let's give it a label star here. Well, because this involves powers of x to the 2n, if I have either plus 1/2 or negative 1/2 to the 2n, that will cancel with my 2 to the 2n, so this is just negative 1 to the n. And this series does not converge. So hence, the interval of convergence which we denote by I, is the open interval from -1/2 to 1/2. So that's our solution. Here's our power series representation of our function, and we determined that it's valid in the interval -1/2 to 1/2. So just notice here what we did in order to determine the interval. The first thing we did was use this property here that we know for the series that we are working from to show that our power series converges whenever x is less than 1/2 in absolute value, but we have to show that the interval can be no bigger than that. So what we did is we took the two endpoints of this interval, x equals 1/2 or x equals -1/2, plugged them into the series here, and showed that they result in a series, so specifically this series here, which doesn't converge. So therefore we know that the interval of convergence must be -1/2, 1/2. Okay, let's do example B. And so for example B, we're going to follow a similar argument. So g of x is equal to x divided by 9 minus x squared. So let's write this as x times by 1 divided by 9 times by 1 minus x divided by 3 all squared. So that I can write as x divided by 9 times by 1 divided by 1 minus x over 3 all squared. And now again, I recognize that the term in brackets is of the form 1 divided by 1 minus something squared. So then I can write this as the sum from n equals 0 to infinity of what that something is. So that's x over 3 squared raised to the power n. So this is x divided by 9 times by the sum from n equals 0 to infinity of x to the 2n divided by 3 to the 2n. And let's write this as the sum from n equals 0 to infinity of x to the 2n plus 1 divided by 3 to the 2n plus 2. So all I did there in the final step is that I just brought the x and the 9 inside and wrote 9 as 3 squared. Okay, so let's determine the interval of convergence. So we know that this holds. For the absolute value of x over 3 squared less than 1, which is equivalent to x squared being less than 9, which is equivalent to the absolute value of x being less than 3. And again, note that if x is equal to -3 or x is equal to +3, then this series here, let's call it star again, diverges. Why is that the case? Well, if I plug x is equal to +3 or -3 into here, so here I have x to the 2n, so that's going to give me 3 to the 2n, that'll cancel with this. So what I'm going to end up with are terms that aren't tending to 0 as n tends to infinity. So from that I can immediately conclude that my series is diverging. So from this we conclude the interval of convergence is I equals -3 to 3, okay, and it's the open interval. Okay, so again, this was an example of the same procedure. So exactly like in part A, what we did was we reduced the function g to something of the form some numbers times by 1 divided by 1 minus some function of x, and then we expanded it using the power series of 1 divided by 1 minus x. Okay, so what we've seen in these examples is that if you have a function that looks something like 1 divided by 1 minus a function of x, then you can find its power series expansion, okay? Just by using what you know for the power series expansion of 1 over 1 minus x. So there's another way in which we can try and build power series expansions, and that's by differentiating and integrating. We're going to see more general ways which to think of power series in the next section, but before we do that, it's useful to have the following result. Okay? And so this result is what's called term-by-term differentiation or integration of power series. So suppose I have a power series. Okay, so this is power series Cn x minus a to the n. Okay, so this is a power series centered at a. Doesn't need to be centered at 0. And the coefficients are Cn. And suppose this has radius convergence r. Okay, so that means that it converges for all x that are within r of the point A, okay, because the series is centered at A. And now let's define the function f of x is equal to the power series. Okay, so in other words, we're saying that this power series is the power series representation of x. Then this function f is differentiable on the interval of convergence of the power series. So the interval of convergence of the power series is this interval here. Okay, so it's the interval around the point A of radius r. And moreover, its derivative is given by this power series here. Okay, so it's the sum from n equals 1 to infinity of n times Cn times x minus a to the n minus 1. So the key point here is that the terms, this term in the series is just what you get if you differentiate this term. Okay? So if I differentiate this term here, I get a factor of n coming up here, and then my exponent drops from x minus a to the n to x minus a to the n minus 1. So in effect, what we're saying is that if you want to differentiate a function and you have its power series representation, what you do is you just differentiate the power series term by term. Similarly, if we want to evaluate the indefinite integral of f, then what we do is we integrate the power series term by term. So here, the integral of f of x dx is equal to an arbitrary constant c, okay, because it's an indefinite integral, plus this power series here where we have Cn and then we have x minus a to the n plus 1 divided by n plus 1. And if you look at the power series we started with, you'll just notice that this term here comes from integrating the general term of this power series. So we just integrate term by term. Finally, both these power series, okay, so the power series for f prime and the power series for the antiderivative, or the indefinite integral of f, they both have the same radius of convergence. So to reiterate, what this theorem says is that if you have a function represented as power series with a radius of convergence r, then if you want to differentiate or integrate that function, you can do that by differentiating or integrating the power series in a term-by-term way. Okay, let's see how to use this to find power series of a couple more complicated functions. So here, let's take example A to begin with. And so here we have the function f of x is equal to 1 divided by 1 minus x squared. So this function, we can't use the trick that we were using previously because it's not of the form 1 divided by 1 minus something. Okay, it's of the form 1 divided by 1 minus x all squared. But what we can do is we can note that f of x is just the derivative, d by dx, of 1 over 1 minus x. So we know that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n for the absolute value of x less than 1. So therefore, using part A of the above theorem, the power series representation of f of x can be obtained by just differentiating term by term this power series here. So this gives us n times x to the n minus 1. And this holds for absolute value of x less than 1. So just one small thing to notice here, this is a very minor point. So I didn't state this in the theorem, but let me say this now. So if you look at the theorem here, the series goes from n equals 1 to infinity. Here I've written it n equals 0 to infinity. Don't be alarmed by this at all. Just notice that the first term in this series here is n times by something, so it's equal to 0. Okay. So if you prefer, we can just write this as n equals 1. Okay, let's do example B. So now we have g of x is ln 1 plus x, and we know that ln of 1 plus x is an antiderivative of 1 over 1 plus x. So we can write ln of 1 plus x as the indefinite integral of 1 divided by 1 plus x. Well, we know that 1 over 1 plus x is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the n, for absolute value of x less than 1. So that's the example that we started today's lecture with. So therefore, g of x is equal to, we just integrate term by term, and I'm going to write this over here. This is going to give g of x is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the n plus 1 divided by n plus 1. And this is for absolute value of x less than 1. So all we did here is we integrated each term of the power series here. So if I integrate x to the n, I get x to the n plus 1 divided by n plus 1, and this holds for whenever the absolute value of x is less than 1. Okay, finally let's do one more. So let's do example C here. So now we have h of x is equal to arctan x. And we all remember from back earlier in the course that arctan x is an antiderivative of 1 divided by 1 plus x squared. So, what do we know? Well, if I take 1 divided by 1 plus x squared, I can write this exactly as we've done several times in this lecture already, as 1 divided by 1 minus negative x squared. So then this becomes the sum from n equals 0 to infinity of negative 1 to the n times by x to the 2n. And this holds for negative x squared in absolute value less than 1, which is equivalent to the absolute value of x being less than 1. So therefore, we've determined that h of x is an antiderivative of 1 over 1 plus x squared. We've found the power series representation of 1 divided by 1 plus x squared. So therefore, to find the power series representation of h of x, we just integrate term by term in this power series. So that's going to give us the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1. Okay. And again, this is going to converge due to the theorem. This converges with or has the same radius convergence as the series that we're integrating. So this series has radius convergence 1. So the same is true for the power series that we get for h of x. So, to conclude today's lecture, what we've seen is a number of different ways of constructing power series representations of functions. We started by doing this by representing functions that were similar to 1 divided by 1 minus x. Now what we've seen in this last couple of examples is how to integrate and differentiate power series. And what you're going to see in the next lecture is how to relate power series to functions in the general setting. So that's it for today, and then in the next class you'll be moving on to Taylor and Maclaurin series.